I will talk about the recent work we have been doing in the last year about selfish mining. And essentially, I'm going to explain first what is the profitability model and the different mathematical models that are used to analyze selfish mining with their properties, their advantages and disadvantages. Now, we started with a paper about a year ago where we kind of clear up what is the profitability model, and started with the Martingale techniques that I'm going to talk about a little bit, and we apply this to different block withholding strategies. There are several types of selfish mining attacks. So in particular, stubborn mining and trailing mining. So we have two other papers on this where we compute the exact formulas for the profitabilities. And then we realized that if you are only interested in long-term profitability, like what you used to do with the previous Markov models, you have a very direct combinatorial approach with involves quite nice mathematics of Catalan numbers, Dyck words that I'm going to talk a little bit about. And we applied this both to Bitcoin and Ethereum. And we have a whole paper also of selfish mining in Ethereum, which is combinatorically more complex. And it's kind of interesting because it shows something that we noticed at the beginning, that selfish mining really is an attack on the difficulty adjustment formula. So let me explain a little bit. Well, this is to summarize the results that we have for Bitcoin, this picture. So I'm going to explain this at the end. This is essentially the parameter space with the hash rate of the selfish miner and the constant gamma that measures, a constant between 0 and 1, that measures the connectivity of the selfish miner to the network. And for each point in parameter space, we have a strategy that is best than the others, and you get a picture like this. So I will explain this in the talk. So first, we need to understand what is profitability. And well, many of you here have businesses, and what is important in the profit and loss balance is not just the abstract profit and loss, but the profit and loss per unit of time. You care about what you make in a month, not what you make in your life, all right? So this is important to formalize it mathematically. We want to do mathematics. We are mathematicians, and we would like to have a model first that is as accurate as possible. So profit and loss is revenue minus cost. And when you run a mining operation, you have a lot of different costs: energy, hardware, salary of employees, etc. And then you have revenue that comes essentially from the block rewards, the mining fees, etc. Now, we have to put in the picture the time considerations. Otherwise, you know, it's not just a matter of mining more blocks in proportion, a larger proportion of blocks than before, is how long it takes to mine these blocks. Okay, if I mine 90% of the blocks, but I slow down the network so that I do this in a year, so it doesn't, I mean, if I increase the validation time, etc., is not profitable. And this is exactly what happens with selfish mining, where you withhold blocks, so you slow down the network. And you have to compute that and take this into account to have a good picture of profitability. So time considerations is essential, and then you have the long-term profit and loss, which is just the limit of this revenue over time minus the cost divided by the time, all right? So we have a model of repetition games. This comes from gambling. You have a profitable strategy, and you repeat it over cycles. So we consider 3 random variables. One is the revenue per cycle. So a cycle, it means that we start at some situation, and after some time, we return to the initial situation, so we can start again. It's like if you play some strategy in the roulette, you apply one time, and then you renew it, etc. If it's profitable, you will repeat it infinitely often to get a benefit. So we have the revenue per cycle, the cost per cycle, and what is important, the time per cycle, the time it takes to fill the cycle, to return to the initial state. Now, we look at integrable games, which on average, this expected time is finite. If you have a strategy that takes forever, you can compute very few things, all right? And it's not profitable if you don't return to the initial state. The goal is to repeat it over and over. And well, there's a very, indeed, simple theorem, is that the long-term profitability is just this given by the expectation of revenue minus cost divided by expectation of time. So this is the model. This is just the strong law of large numbers for those that remember some of their classes of probability. And when we compare different mining strategies, we realize an important fact is that first we have what we call the revenue ratio, so the expectation of revenue by unit of time, and the cost ratio, the expectation of cost by unit of time. And if we want to compare two strategies with the same cost, the same epsilons here, is the cost ratio, then we just need to compare the gammas, okay? So you have two strategies. Maybe you don't know much about the cost, but you know that both have the same cost. And this is what is going to happen in selfish mining, that mining honestly or mining dishonestly, selfish mining dishonestly, keeping blocks and releasing them at the appropriate moment, has the same mining costs. Okay? So essentially, to compare both strategies, we only need to compare the revenue ratio. And this is an important observation. Very simple, but very important observation, so that we can really start doing mathematics. So, you know, the protocol rules tell the miners that they should release the blocks once they found a solution to the hash problem. And, but nobody's going to force them. There is no police in the network, and they can just withhold these blocks and release them at the appropriate moment. Naively, this seems to be not a very interesting situation because you run into the risk of losing your block reward. You keep your block and then another mines a block and your block is not of any use. So you don't get any revenue, at least in Bitcoin, for this orphan block. Now, the selfish mining strategy in general is to keep this block and release it at the appropriate time, and you have different algorithms and different strategies how you can release them. The goal is to build an advantage. If you are not able to build an advantage, then you start with the initial situation mining on the public blockchain. So when you build an advantage, you keep building the advantage, and when the honest miners mine a block, you can release, for example, 2 blocks and invalidate their block. So as you see, these strategies create a lot of orphan blocks, and it slows down the network. And in the way you release the block, you can maybe not release just the blocks 2 by 2, but just wait that the public network catches your secret fork and then release them at the same moment. So depending how you decide how to release the blocks, it gives different strategies that have different profitabilities. You can be even more risky and even allow the public block to go ahead of your secret fork and hope to catch up. Even though your hash rate is always supposed to be less than 50%, because otherwise you can just rewrite the whole blockchain and overrun any public blocks that you like. Okay? Now, so we have different release algorithms, and the key observation is that, I was telling you, is that block withholding and honest strategies have exactly the same cost as long as you run your machines full-time, okay? So the epsilons there of the cost ratio are the same, and we only need to compute the revenue ratios. So other important observations, so sometimes people are confused, is that the costs and the exchange rate of the coin doesn't influence this analysis. Doesn't matter. This analysis is independent of the market price of the Bitcoin. Now, all these external factors that make very difficult to evaluate the cost do not play into the picture because we are just comparing the strategies. So this goes into the epsilons. So make a model. To make a model for the cost is hard. It's difficult. It's a problem of finance and economics. It's not a problem of mathematics. And, but we don't need, fortunately, we don't need this analysis, a model of the cost, in order to compare the strategies. So this just to be clear on that. Now, what is the profitability of this block withholding? So we'll say that it's profitable if we beat the profitability of honest mining. And for honest mining, the cycles are very simple. You keep mining, and if you mine a block, you release it, so you get a reward. If someone else mines a block, then we accept the new block in the blockchain, and we start again mining on top of this new block. So the cycles are very simple. Or I win, or the other miners win, and then we can look at the probability of having a block, mining a block, or the honest mining a block, and we can compute the expected revenue, and so it's very simple. Now, we have an important theorem. Well, I think it's important because, for mathematicians, because we can prove something that is kind of fundamental in the Bitcoin protocol. You expect the Bitcoin protocol to run in a stable way. That means that the protocol rules are online with the individual in private interest of the participants in the network. This is the only way you can guarantee that the protocol works without a police or sanctions. That will imply some centralization. So you expect that the rules is that the optimal strategy is to release the blocks. And strictly speaking, this is what we expect, but this is not true. But it's true if we make a condition. Without a difficulty adjustment, if we don't touch to the difficulty, there is no block withholding strategy that is more profitable than honest mining. And this is quite satisfactory. But it also shows that there is some problem with difficulty adjustments. And in order to prove this result, you have to use some kind of non-trivial mathematical theory. It's a problem which is similar to the problem of Martingale playing in the casino. Okay, you can play roulette, and if you lose, you double up your bet, etc., until you win, and then you make some profit. This doesn't work because there is a limit on the bets, and also because a mathematical theory that is going to prove that precisely whatever strategy you can imagine, and there are infinite many strategies that you can imagine, no strategy is going to be the hedge of the house. So here is the same. And for this, we use what is called Martingale techniques, and well, in particular, a result that is called dope stopping time argument that allows you to prove this type of result, okay? Now, we have to look at the situation, what happens when we have a difficulty adjustment as we do. That is necessary for other reasons. And, well, the corollary of this theorem is that the selfish mining attacks are an attack on the difficulty adjustment formula. It's because the difficulty adjustment formula is not built properly that these attacks can theoretically exist. And I say theoretically because really we don't observe them. If you start to selfish mine and you invalidate plenty of blocks, you can see many orphan blocks, and of course there will be a reaction. So these are kind of theoretical attacks, but in practice it can happen. It can happen in some covered way. Anyway, the attack is on the difficulty adjustment. So the problem with the difficulty adjustment is that it does not account for the orphan blocks. You know, you count how many blocks have been validated in Bitcoin during the last 2016 blocks, and you look the time it has taken, and you can estimate in that way the hash rate of the network. But if there are many orphan blocks, these orphan blocks have consumed a lot of hash rate, and they are not taken into account. So just the estimation of the hash rate by counting the number of blocks divided by the time doesn't account to the full hash rate, and because of the orphan blocks. Now, the solution is to include in the difficulty adjustment formula these orphan blocks. And for this, you need to know that they exist. Okay, you don't know that they exist in the blockchain. Okay, they disappear from the blockchain, but we have a brief proposal. If really there is a problem with selfish mining, the miners, the honest miners, could signal the orphan blocks so that in the next difficulty adjustment formula is taken into account. So the new formula will be that the difficulty, this n prime is the number of orphan blocks that are signaled in these 2016 blocks, these 2 weeks, in average 2 weeks period. So you just add these in the new difficulty, okay? And if you do this, if you implement this BIP, which entails a hard fork, then there is no risk of selfish mining, and then the theorem of stability becomes a theory unconditional. There is no longer a problem with difficulty adjustment because you correct it in the proper way, okay? Well, this is just a proposal that we have in the first paper. Now, the classical Markov model consists in, well, first we fix some parameters, which Q is the hash rate of the attacker, of the selfish miner, and gamma is the connectivity. The connectivity is the probability that when you release a block, the number, if there are 2 competing blocks, so you notice that the honest miners have released a block, and you simultaneously release your hidden block, and then you look at the proportion of miners that will join you. Okay, so it's something in between 0 and 1, and this is called gamma, the connectivity of the attacker. It depends essentially on how well it's connected to the network. And the Markov model, you know, the Markov models are discrete models, discrete states models, where you have a probability of jumping from one state to the other. So the chain state is defined by the length of the secret fork and the length of the official blockchain, essentially. And what you do is you can compute this probability of passing from one state to the other. And these models are good to compute the long-term profitability, okay? Because it will give you the proportion of blocks mined by the selfish miner, and once the difficulty adjusts, then it will give you the profitability, the revenue ratio. But it cannot provide, in this Markov model, we know that we jump from one state to the other, but we have no information about how long it takes, about the T time, okay? And of course, if we have a Markov model for which it takes infinitely often to go from one state to the other, then the profitability by unit of time goes down. So some basic practical questions is that when we start selfish mining, as we have seen for the theorem, before a difficulty adjustment is not profitable. And once we have the difficulty adjustment, it will become profitable. But how long it takes for selfish mining to enter profitability? These are some basic questions that you need some Martingale techniques in order to answer. You cannot answer this with the Markov model, all right? Now, in the Martingale model, you just make the standard model for mining. You look at the number of blocks at time t mined by the honest miners and n prime t by the selfish miners. And these are Poisson processes. That means that for a given t, this follows a Poisson distribution with parameters alpha and alpha prime that are related to Q. Q and P, which is 1 minus Q. And if you want, the type of theorem that we have is the following. We call these Poisson races. Is that we have these 2 independent Poisson processes with parameters alpha prime and alpha. Alpha prime is less than alpha. This means that Q is less than 1/2. And we start with the same number of, at 0 is the starting time, the starting of the race, no blocks mined. And then we look at what we call the stopping time. The first time that NT is ahead n prime t. Okay? This, in some sense, is going to allow us to compute the expectation of the time of the cycles. So we assume that this stopping time is finite almost surely, which is true in this situation. It's a theorem, and it's integrable. And we can compute the expectation of t, and as well as the expectation of tau, the stopping time, as well as the expectation of fn prime tau and tau. So it means that in this very simple situation where you have 2 pure Poisson processes, you will be able, using this theorem, to compute the expectation of tau, the average time it takes for n to go over n prime, and as well as the number of blocks that you will mine. So using this, you can start proving and computing the revenue ratios. Now, so for example, an application, if we have a 10% hash rate and a connectivity of 90%, which is quite good, how long it will take to enter profitability? Well, it would take about 10 weeks, which is 5 times the usual period. And the reason is that you selfish mine, you slow down the network, and the difficulty adjustment comes later. So if you plan to selfish mine in Bitcoin with these parameters, you should keep some money, okay? Because you will be, during this 10-week period, you will make more money honest mining than selfish mining. Now, so as I said, it's impossible to obtain this type of results with the Markov model approach. And indeed, if what you are interested is in the long-time profitability, so just the Markov model results, we have a better way to get them. And this is what I want to present. And it's a way with combinatorics, which uses what we call Dyck words, Catalan numbers, and Catalan distributions, which are objects that appear everywhere in mathematics. And, well, we were quite happy to find the connection with these classical objects with Bitcoin. Now, Catalan numbers. These numbers were first studied by Euler and Segner. They were called Euler-Segner numbers before the 20th century. Then Catalan wrote a couple of papers, very interesting ones on Catalan numbers, and the people started calling them Catalan numbers. And this can be shortly defined just by this formula, so 2n factorial. I recall that the factorial is just, the n factorial is to make the product of the integers up to n, and you divide by n factorial. This doesn't look like a whole number, but it's a whole number, and you can compute the first numbers of this sequence, C0 equal 1, C1 equal 1, C2 equal 2, etc. It grows pretty fast indeed. And you can write down the generating series. So it's a classical way in combinatorics to encode combinatorical properties. You write down the generating series, and you translate combinatorical recurrence properties, etc., with functional equations with the generating series. This generating series for Catalan numbers was found by Binet in the 19th century. And in the Bitcoin problems that we are going to look, what appears is this Catalan distribution. So you can, with these numbers, you can build probability distributions, and this is just says that the probability is 1. Okay, so you have 2 main Catalan distributions that appear. Now, okay, maybe I should give you other definitions of Catalan numbers that are less mathematical, or maybe more. I don't know. The first one is the definition that an algebraic topologist would prefer. You take a convex polygon with n plus 2 sides, and you look at all the triangulations. So you look at all the ways of cutting this polygon and dividing it into triangles. And you count how many numbers you have exactly Cn, the Catalan number. So this is the original approach by Euler. He was studying exactly this problem. How many ways you have to cut a polygon of n sides, convex polygon of n sides into triangles. Now, you have another way of defining Catalan numbers. It's a number of paths on a lattice. So I consider a lattice and an n by n square. I look at monotonic paths. So this means that I can only go to the right and up, only right and up, and I look the number of paths connecting one vertex to the opposite, to the diagonal opposite vertex, without crossing the diagonal. Okay? So if I count, here is the case of n equal 4, and I have 14 possibilities. Before I have a polygon of size 6, n plus 2, I have these 14 possibilities. Okay? So it's the way of counting. Okay. Now there is another definition that maybe computer scientists prefer. If I take a full binary tree, so this means a binary tree, it has 2 branches at its vertex, or no branches. This is why it's called full. And if I have n plus 1 leaves, then the number of trees of this sort is Cn. So here is the case C4. So C4 was equal to 5, I think, okay. So there's another possibility. And then finally, there is another definition I can take. All of these definitions are equivalent. Is the number of Dyck words of length 2n. So what is a Dyck word? So I build a Dyck word with 2 letters, S and H, S for selfish, H for honest. And I just write a string, a word, with 2n letters. And I'm going to assume that each pre-string, pre-word, has more S's than H's. So if I take n equals 3 here, I have exactly these 5 big words, okay? And it's exactly the number of C3 equals 5, okay? So this is the way we are going to use in order to compute the probabilities of selfish mining. Okay, so once we have this first combinatorics, I call D the space of D words, and the Catalan distributions define indeed probability measures on D. And what is the relation with selfish mining is that an attack cycle is described by the chronological order of discoveries of blocks by the selfish miner and by the honest miner. So this doesn't mean that they release it, right? This could be blocks that the selfish miner mines and keeps secret. But we can look at the chronological appearance. And we have a probability once in a given state, the probability that the selfish miner mines the next block is Q. The probability as the honest miner mines the next block is P, with P equal to 1 minus Q. Now, what is the relation with the classical selfish mining algorithm is that the attack cycles of the selfish mining strategies are of this 4 form. All is H, just H. It means that we start selfish mining, but then the honest miners mine the first block, so we start again, all right? Very simple cycle. Or SHH, so we mine a first block, and then the honest miners mine 2 blocks, all right? Then we start again. Or SHS, or the final possibility is that we take an advantage, SS, and then we have a dig word, W, and then a final H miners when the honest miners catch up. All right. So having this, for example, if I look at this dig word, it describes an attack cycle which has a probability. So to compute the probability, I count how many S's I have. I put Q to the power of the number of S's and H to the power, P to the power of number of H's. Now, a corollary of this analysis is that I can compute the number of official blocks added to the blockchain after an attack cycle. So, and this number, okay, this is the number of official blocks mined by the selfish miner, all right? This is essential part of computing the revenue of the selfish miner, and I can compute it explicitly just using this simple combinatorics. But you see, here what it appears is the Catalan number appears here, and the Catalan distributions will appear here, all right? So once you have this, you can also compute the distribution Z of the number of blocks that the attacker adds to the blockchain, and we can express the revenue ratio. So I make it in units B over T0, which is the profitability of the honest mining, and we can recover this formula for the long-term revenue ratio. Now we can apply this, it's a very simple proof, all right? It's something that will fit in half a page to once you set up the problem, you can compute this in very quickly. Indeed, in a couple of lines, once you have the intermediary results. So you get this, so you see gamma that appears here, and then the rest depends on P and Q, essentially on Q. P is 1 minus Q. Now, for the other classical block withholding strategies that were invented by Miller and his co-authors, so they have a paper where they studied these profitabilities numerically. So we can also find closed formulas for the revenue ratio. So here the closed formula for the lead stubborn mining strategy, and this other one is this equal fork stubborn mining strategy. So you have explicit formulas. What appears here is the generating function of Catalan numbers. C is the generating function of Catalan numbers. Okay? Now, we can compare these strategies, and also there's another strategy that I don't give the formula because it doesn't fit in the slide, but we have computed it, is the trailing mining strategies where you allow the official blockchain to take some advantage. So A blocks of advantage. So we have the parameter space here, Q and gamma, and honest mining is here. So if you don't have enough hash rate, honest mining is the best one, but as long as you go over 30% here, you have all these selfish mining strategies, lead stubborn, which is very thin here, and equal fork stubborn, and then here the trailing mining strategies. So you have a full picture of best strategy, the comparison of all these strategies for different parameter values. Now, so I want to just comment on the last work on the Ethereum mining strategies. It's interesting to study Ethereum and other cryptocurrencies to understand better Bitcoin, because they have a different type of proof of, reward system. They take uncles into account, which uncles are on-farm blocks that are directly attached to a block in the main blockchain, and nephews, and when you sign out one of these blocks, you get some reward. This makes the combinatorics much more complicated, but on the other hand, we have the combinatorial tools with big words to deal with it. Now, also a difficulty that appears is that one selfish mining strategy, the way you release blocks, is no longer equivalent. In Bitcoin it was equivalent, but in Ethereum it's not equivalent because of these signaling blocks. So there are different variations of the classical selfish mining strategy. You have a first strategy, which we call maximum belligerence and signal all uncles. So the goal is to maximize the revenue. Others is minimum belligerence and signal all uncles, or minimum belligerence and signal no uncles. So the goal here of this last one is to minimize the difficulty adjustment. Sorry, so to make it to make the difficulty as low as you can. Okay? So you have two factors here, or you make more money by revenue, or you lower the difficulty so the attack is more effective. So what we found is that the best strategy for a hash rate larger than 25% is to avoid competitions and ignore uncles. So you don't sign out uncles. So this really shows very graphically that the selfish mining attack is an attack on the difficulty adjustment formula. So we can also look at on parameter space at different regions. So honest mining, you have the second strategy, 2i strategy and 2b strategy. The first strategy is never profitable on the parameter space. Now, the conclusions is that first, the revenue ratio is the correct objective function to look at. And what should be clear from these examples and this analysis is that the selfish mining is really an attack on the difficulty adjustment formula. We have this B proposal that can be implemented in case we found really that there is a problem with selfish mining of some miners. The Martingale approach gives really the full picture. It involves more mathematical material and mathematical theory, but it gives we can get the full analysis. For computation of these long-term profitabilities, the Markov approach that is good, but can be replaced by this more direct combinatorial approach with big words. And the long-term profitabilities of Ethereum confirm really that selfish mining is an attack on the difficulty adjustment formula. So I think I am ending up here, and I am open for your questions.
Thank you. I have a question about, let's say there is, you as a miner, you have more than 30%, I think, of the hash power, but there's also another adversarial mining pool or miner that also has about equal amount of hash power. Would the strategy then differ?
Yeah, well, I mean, the situation we are considering is the classical situation where you have only one selfish miner of pool, right, that is behaving dishonestly, and the rest are behaving honestly. Of course, there are more complicated situations, like, for example, there are several selfish miners. And then it depends very much on how much hash rate they have individually and together, and if they collaborate or not, etc. So imagine that everybody is selfish mining. Then the selfish mining is not interesting because the network stalls. Nobody releases the blocks, right?
Yeah, exactly.
And so nobody makes a profit. So these situations are far more complex. We have the tools to analyze quite a bit the multiple player situation, but it's more complex. Also involves some game theory to make some assumptions on if they're coordinated or not. But thank you for the question. Of course, this only ends up let's say, the classical, very simple situation with one selfish miner and the others, but the field to understand all the possibilities is wide open.
Right, I have another question, if that's fine. Have you already also tested or simulated on...
Yeah, indeed there are people that have simulators. You can find 2 simulators online that can confirm, I mean, you can confirm the results. Well, we mathematicians, we don't need simulators. Once we prove it, right? Unless the proof is wrong, and so we have a proof that is checked. But it's nice to check with the simulators that you recover these results. So sometimes the simulations that have been done before, they do with Monte Carlo, so sometimes the precision is not. So if you look at the Miller and Company paper, you have this picture of different regions, but the frontier, the boundary is blurry, right? And this is because when you run a Monte Carlo, you need to run it many times in order to get a precise picture. But yeah, there are 2 simulators online. You can find them, and it's nice to play with it.
Thank you for a very interesting talk, a very interesting way to look at the selfish mining problem. I had a question about the BIP proposal. One thing that occurred to me is that it's probably not viable as a soft fork, so it would have to be...
No, it's a hard fork. Anything you touch to the difficulty adjustment formula, it's a hard fork for sure.
Okay, yeah.
I think did I say soft fork? It's hard fork.
You didn't specify. I was just curious.
No, it's a hard fork. If you touch to the difficulty adjustment formula, it must be a hard fork.
All right.
It's implemented in the code, yeah.
Hey, Ricardo, great talk. So I was wondering about using the frameworks that you've laid out to look for other candidate difficulty adjustment block periods. Like, is there a way that you can search through that parameter space to find other plausible difficulty algorithm adjustment windows that would minimize the success of selfish and stubborn and trading strategies?
Sorry, your question is about the difficulty adjustment formula or about other selfish mining strategies?
The window specifically, if you can find a more optimal window that would reduce the success of attacks.
Good question. Indeed, I mean, if you fix from the beginning the selfish mining strategy and you decide that you are going to allow the official blockchain to be in advance of your secret fork, but you fix this number, then the picture I gave you the optimal picture. Okay, all the optimal strategies among them. Now, you can be more creative and say, well, depending on the stake, because I mean, if I have a long secret fork, even if I have a big disadvantage, it may be interesting to continue mining. So there have been some numerical studies of Eyal, Sompolinsky, etc., on these other more general optimal strategies. But it's numerical. So numerically, you can see that, and even theoretically, that you can allow arbitrarily long disadvantage and it's still profitable. So this you can analyze numerically using these Markov decision processes. Okay. Now, otherwise, there are many other possibilities for attacking the network. Is that something we are assuming that we work in a closed hash rate environment, but it's not true, because you start selfish mining, you lower the difficulty, and then other people that were mining other coins will come. Okay, so this is also a situation where, in practice, fights against selfish mining, and what counts is not the hash rate, the relative hash rate you have in your coin, but if there are other coins that have the same proof of work algorithm, it counts. This hash rate counts because people can come. This is also an observation that we made, is that indeed, to have other coins that have the same selfish mining algorithm is a weakness for all these coins. Okay? So indeed, people should, if they will new coins, they should, for their own interest and the interest of the others, should modify the selfish mining algorithm so that the same hardware and the same material cannot be used for mining both. I mean, the thing is to avoid that miners can switch quickly from one to the other. And we have seen this complicated dynamical situation with Bitcoin Cash and Bitcoin, and people that were switching mining one in the other, and then they had the difficulty and the hash rate of Bitcoin Cash was kind of chaotic, right? Which is very interesting for dynamical systems. That is my field of expertise. I mean, that gives a very chaotic system. Okay, But yeah, I mean, the idea is that it's better for everyone if different coins have different mining algorithms. I don't know if that's a question. Oh, we have to handle. Okay, thank you to you.